Hello everybody, I am the heavy metal chemist and I'm going to try and do another lecture today. This one I'll be covering the electrophilic addition of various things to carbon-carbon double bonds. This is kind of a follow-on from my previous lecture where I talked about orbital hybridization. Again, forgive the pen and paper, but I've still not managed to get my graphics tablet working. This is a fairly simple concept to understand. If we've got an alkene, like ethene for instance, and say we bring bromine along to it. Now, as I covered last time, draw it in lightly, ethene has a nice big pile of electrons sat above and below the plane of the molecule in the form of a carbon-carbon double bond, and bromine, being a halogen, is fairly oxidizing species, which is why we call it an electrophile. It likes electrons. So if you've covered van der Waals forces, what you'll realise is that as the bromine approaches the ethane, you get a slight delta plus charge there, and delta minus charge there. Now, electrons, being negatively charged, are attracted to the bromine, and what we get, this curly arrow here represents the movement of a pair of electrons, not one electron. What you get is the electrons from the double bond, just the double bond, not all four electrons, attack this bromine, and then the bromine-bromine single bond breaks, and then what we end up with is H, with the Br there, H there, H there, and not bromine there. That's a positive charge on that carbon, and a negative bromide ion, and then that pushes, it's maybe not quite as clear as it could be, that bromine attacks there, and you end up ultimately with H, 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 dibromoethane, like so. So basically what we've done here, if I go back to the previous lecture, is we've converted these two carbons, which were sp2, into sp3, and we've added bromine across the double bond. Now, there's a number of other species which can do this, notable one being the hydrohalic acids. So if I flip to a new page, there are some rules associated with this kind of reaction. So we'll just start again with ethane. H, 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 Br, H. Right, now here, because bromine is more electronegative than hydrogen is, we have a permanent dipole on this molecule, and what we end up with is that happening, which gives, sorry, get rid of that. Then positive charge there, and then from that, again, it's quite simple. The bromine attacks there to give H, 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 Br, like so, monobromoethane. Now, there are a number of rules associated with this process. Because this is a symmetrical molecule, you don't end up with any selectivity problems, but if we have an asymmetric alkene, such as propene, or something along those lines, we have another problem, because that way you could end up with two different products, either with the bromine there, bromine there. I'll just draw the little branches on to show where the hydrogens are. Now, what we normally see is you won't get a pure reaction with the bromine here. What you end up with is you end up with more of this and less of this. I can't remember the exact ratio off the top of my head, but this is due to what we call charge stabilization, because this, when you end up performing this action here, you end up with a positive charge stabilized like that, and basically the hydrogen atoms around it basically push a bit of electron density into that positive charge and help to stabilize it, whereas if we've got the positive charge at the end, there is less electron density to be shoved in there. And this is called the Markovnikov rule. The easy way that my old chemistry teacher used to tell me to remember it was the carbon that has the more hydrogens already, in which case, with a double bond, this one, will get the extra hydrogen. Or them that has gets. It's a crude way of saying it, but it's fairly good way of remembering things. There are certain compounds which do what's called an anti-Markovnikov addition, but for the most part, this is how it happens. Again, there's a fairly good article on Wikipedia about this reaction mechanism. I just thought I'd explain it in my terms. Now, for those of you studying degree level chemistry, there are a few little extra caveats to this mechanism, which you will be expected to learn. The first bit's more kind of A-level chemistry, effectively. But if we have, say I take propane and we react that with Br2, what we end up with is this is a fairly complicated way of looking at it, but if we take a lone pair from there, what you actually end up with is that happening, which as an intermediate gives you like that, hydrogen, 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 and then Br minus, and then this will ring open this strange three-membered ring here, like so, to give you your dibromo propane. This is more of a degree level mechanism, which you can probably read into a little bit more if you want to, but I can always cover it if anybody wants to request anything. Please do let me know, and I will try and do a video on it for you at some point in the near future. So thanks for watching. Please do subscribe, and I'll hopefully start putting more videos up than I have been doing. I've just been trying to find more post-doc posts at the moment, which is easier said than done because of funding, etc, etc. But yeah, so thanks for watching, and like the video, subscribe, etc, etc. Goodbye.